Hello and welcome to Conversations on AFM. I'm Dr. Elizabeth Kugler, a science communicator and your host of today's first conversation, an interview with an AFM pioneer. Today we will be talking about the technology and history behind Atomic Force Microscopy and Scanning Probe Microscopy, also called SPM. To talk with us about this exciting topic is Professor Mervin Miles from the University of Bristol. He is a Fellow of the Royal Society and expert in innovation of SPM instrumentation for imaging and measurement of biomolecular structures, as well as the development of SPM technologies for non-imaging applications such as sensors and data storage. It is our pleasure today to be talking to Professor Miles, who is an emeritus professor at the University of Bristol and was head of the Nanophysics and Soft Matter Group. He held a prestigious position of Director of the Nanoscience and Quantum Information Centre, as well as being a Royal Society Wolfson Research Merit Award holder. And he's also the co-founder of two spin-out companies in AFM. Thank you so much for being here with us today, Professor Miles.
It's my pleasure. I'm looking forward to it.
So now for our listeners who don't know Scanning Probe Microscopy, or SPM, it is a collective term for techniques such as AFM and Scanning Tunneling Microscopy. So what this means is that these techniques use a probe to scan across the surface of a sample to describe its surface topography and other properties such as tissue stiffness and temperature. Each different SPM technique has various different principles for measuring the interaction between probe and the sample. For example, AFM measures forces between the probe and the sample surface. What makes these techniques so special is that instead of radiation, such as used for light microscopy or magnetic resonance imaging, where we use light and magnetism respectively, in AFM we use probe-to-surface interaction to describe the sample. So if you still think it is very difficult to imagine, because I also struggle with this concept, what I always use as a metaphor is to think about like reading Braille with your fingertips instead of reading letters with your eyes. So you go from light and vision to something more tactile with your fingertips. Central to the functionality of AFM are its nanometer-sized probes. They are remarkable high-precision instruments that have redefined our understanding of material properties at the atomic level. And I always find it hard to put these sizes into perspective. So as a reference, 1 nanometer is 1 billionth of a meter. If it's easier for you to understand, our DNA has a diameter of 2 nanometer. So this is a remarkable resolution. And one of the defining features of AFM is, in addition to this, its adaptability to diverse environments, meaning that it can be used in ambient as well as liquid conditions. So before we start talking with you about the history of AFM a little bit more, maybe you could fill us in a little bit about the gaps that we had in your introduction and about your illustrious career and what excites you about the SPM technologies.
I gave a talk the other day, or a question time, with some kids, some primary school kids, with their parents. And the point was to say why I was doing, how I ended up doing what I do. And I had thought about it for a bit, and I suddenly realized that microscopy in different forms kept cropping up through my whole life, from probably age 10, when I tried to make an optical microscope with my Meccano set, if anybody knows what that is anymore, through to my PhD, when I used a 1,000,000-volt microscope, my postdoc, where I used a 2 kilovolt electron microscope, until I came eventually to scanning tunneling microscopy. And it's like I've had this passion for microscopy ever since I can remember. Looking to see what you can't see normally, with your eyes, but looking into that kind of space that is a bit magical, I think.
I absolutely agree. I've been speaking a few days ago about the extremely small things that we start to unveil and just visualize with microscopy. So it's really great to have an expert like you here today. And we would love for you to explain a little bit more about the theoretical principles or the insights that laid the foundation for AFM.
Yes, of course, AFM came very quickly after STM, scanning tunneling microscopy. And so a lot of the technical developments that were necessary for that, for example, the scanning mechanisms with piezoelectric transducers, which I think probably that those materials just got to about the right stage with poor, good hysteresis, so that scanning was possible in a sensible way. STM, of course, is a quantum mechanical thing requiring measurement of a scanning tunneling current, a very, very sensitive measurement. AFM, of course, on the other hand, is totally mechanical. We're measuring a force. We're measuring a force between a sharp tip and our sample. And if you think about it, I was just musing the other day, why didn't the Victorians invent it? Because it's a mechanical system. In the 19th century, pocket watches anyway, development, mechanics was coming on very well. The optics for measuring the bending of some kind of cantilever they made would have worked. What we're missing, of course, is the computer to record the data. But I'm sure they could have possibly come along with some photographic plates or something to record the signals that they were getting from a reflected beam off a small cantilever. So it's almost a Victorian instrument, but they didn't do it. I think the first mechanical microscope I can think about is one that actually comes from the co-inventor of AFM, Calvin Quate in Stanford University. He invented the scanning acoustic microscope, which again is totally mechanical in its interaction with the sample. The AFM itself, what we're doing with all these scanning probe techniques is measuring some local property with a very sharp tip that is highly localized. And you want whatever property you're measuring to be highly localized, to have a very fast decay curve. So tunneling current has an incredibly fast, every 1/10 of an angstrom that you separate the tip and the sample, the signal changes by an order of magnitude, so extremely sensitive. At AFM, initially using the repulsive force, that is the Pauli exclusion forces, is extremely sensitive too, about the same when you're in repulsion. In the attractive mode, which is used in non-contact, then the signal decays a lot more slowly, but it's still enough to get atomic resolution. So we're looking for something that decays very quickly, that we can measure with a sharp tip, and that tip should be scannable, or the sample should be scannable with respect to it. And I think that's the beginning of AFM.
It is fascinating to listen to you about this, especially as AFM obviously overcame the resolution limitations of optical microscopes. And like you say, it's a mechanical microscope, which is, for many biologists, probably a very different type of microscopy. Because, for example, I myself have, I think 99% of the time, just worked with light microscopy, maybe a little bit of electron microscopy, but the mechanical aspect is absolutely just mind-blowing in terms of scales. So maybe you could talk a little bit about kind of how this mechanical measurement and the overcoming of resolution limitations of conventional optical microscopes is important if we think about the life sciences and how AFM in bio-AFM plays such a big role.
Yes, I think you're right. Of course, optical microscopes are physically limited to about half the wavelength, so about roughly half a micron in resolution, unless you're using confocal or the super resolution fluorescent techniques. But there was a version of optical microscope which parallels very well the scanning tunneling microscope. It's actually an optical analog. And that was actually invented in 1928. So that's the scanning near field optical microscope. So a mechanically scanning system again, but bringing a very small pinhole very close to the sample so that light doesn't diffract before it can be collected. So near field, that's the meaning of the near field. And this guy in Ireland, Edward Singh, proposed this microscope, which would have been this precursor to the scanning tunneling microscope. But of course couldn't make it because he didn't have optical detectors that were sensitive enough. He didn't have a scanning system, but he wrote several papers on how it might be done. And interestingly, that came to fruition shortly after the scanning tunneling microscope in 1984, again at the same laboratory, the IBM labs at Rüschlikon in Switzerland. They managed to build his version of the microscope, the optical version. So the problems that we have, optical doesn't give us the resolution that we need to see at the molecular scale. Electron microscopy does, but everything has to be in a vacuum and dehydrated and hit with high energy electrons. So nothing is still biologically functional. And so the AFM came along. It was able to give us three-dimensional images. Well, maybe I always think I should say 2.5 because we can't see underneath. We see from the top. Three-dimensional images, not in vacuum, but in a liquid, in an aqueous environment, in physiologically relevant environment. And it would give us resolutions up to atomic resolution, very hard in biological systems, but we did it with some. And at the same time, you could measure other properties. You could measure fluorescence if you wanted. You could measure mechanical properties, all within the same scan. And so it's possible then to follow a process, not only look at the structure in 2.5, 3 dimensions, but you could also change things. You could change the pH, you could change the ionic strength, or you could add an enzyme, and you could see how things happen. And that was a wonderful opportunity because it just opened up the whole of biomolecular systems to the study of processes as well as looking at structures.
And obviously it was such a groundbreaking approach, right?
Yeah.
And you mentioned to us before a little bit about like having the honor to meet the later Nobel Prize winner. But for the listeners who don't know, in 1986, the Nobel Prize in Physics was actually divided. And so one half was awarded to Ernst Ruska for his fundamental work in electron optics and for the design of the first electron microscope. And the other half was awarded jointly to Gerd Binning and Heinrich Rohrer for the design of the scanning tunneling microscope. And so you mentioned before to me that you had the honor to meet Heinrich Rohrer. So maybe you can tell us a little bit about like how was it that you met him and how that changed your life?
Yes, so it was 1984 that I met him. I think it was the first European Biophysics Congress, and it was held in Bristol. I knew Bristol a bit, though at that time I wasn't working there because I'd been a postdoc at the physics department in Bristol. And with my interest in microscopy, I was keen to follow all sorts of microscopy, especially X-ray, because again, X-ray would be possible to do in different environments. And so I went along to a whole session on X-ray microscopy and what the developments were, how they were making the lenses and so on for this imaging technique. And at the end of it, I walked out and was heading for the next session. And I happened to walk out with Heinrich Rohrer, and he asked me if I knew where the next session was. And that was over in the harbour in Bristol in the watershed. And so, yeah, I took him over and, making small talk along the way. So what do you do? What's your interest in microscopy? He explained about the scanning tunneling microscope to me, where you bring this very sharp tip very close to the surface within an angstrom or so. You apply a voltage difference of about a volt or so, and you measure the currents, the quantum mechanical tunneling current, as you scan the probe over the surface of the sample. And that sounded absolutely amazing. And I just thought, well, this is amazing if this can work, because this is such a difficult thing to do mechanically, to scan a sharp wire within an angstrom without touching the surface, without damaging the sample over the surface and create an image. This is amazing. And I kind of was really wondering if they'd actually done it. So I went away and when I got back to the lab, I looked up their papers, and sure enough, they'd got some images of silicon, the original 7x7 reconstruction. And it was convincing that this was the start of something very important. And so from that time on, I was lobbying for my lab there to get the funding to buy one of these microscopes, so we could start looking at biological things right from the start. And interestingly, one of my former colleagues, when I was a postdoc in Bristol, Mark Welland, became a professor in Cambridge, and so I was able to. He'd worked in IBM, and he'd built his own scanning tunneling microscope. So I was able to get some time with him on that microscope, and we looked at the protein I'd been doing X-ray work on. And amazingly, within 15 minutes in the scanning tunneling microscope, we could see individual protein molecules with the right symmetry that I'd been predicting for my X-ray work. And they were like everywhere. And you realize this isn't just luck. This is going to be something that's I should switch my career from X-rays to scanning tunneling microscopy. So that's before atomic force came along. So it was a lot harder to do than atomic force microscopy. And actually, we don't really know why we get images even, because these things are not conducting those proteins.
Amazing and mind-blowing, that story. Like, you were right in the middle of history. So you said you were looking at proteins from the very start. I'm really interested because I thought like it started really off more with material sciences, and then later on people would more like look at protein structures. So was that like really an application from the start, that people looked at protein structures from the start, or was what was like the main application at the beginning that people looked at?
With STM, of course, the sample has to be conducting or semi-conducting, or at least we believed so. Obviously, the proteins and the polysaccharides and things that we looked at aren't. And the reason that we image them is still controversial and debatable. But it was possible to see these structures. Maybe the height resolution is not clear why it's those kind of values. I was at that time working in the Institute of Food Research in Norwich, and it was such a wonderful setting because there were experts on proteins, on polysaccharides, on lipids, on DNA, and so all the teams were very keen to prepare samples for me. So I spent probably 7 days a week, not 24 hours, but quite a lot of hours trying all these different systems in the scanning tunneling microscope.
I hope you haven't slept in the lab, because many people do that when they're like really into the project.
No, it's too exciting to sleep. Keep going.
God, yes, absolutely. That's so great. But actually, did you then, so when you started in X-ray, right, and then you became interested into STM, did you really kind of make a full switch, or did you maybe also like look at the same structures in both methods and then try to overlap them and understand how they compare?
Yeah, try to overlap was the point, really, because I was really looking at small angle X-ray scattering using the synchrotron to provide the source and the high resolution small angle X-ray information. But that's always an indirect method. You're basically having to guess a model, calculate the scattering curve, and check how it matches to the measured curve. And that's never really that satisfactory, because you never can be sure there isn't another model that would also fit quite well. And so to have the confirmation of an image of an individual molecule is incredibly helpful. And I think in some ways we were quite fortunate that the first molecule did work. We took a lot of trouble. Mark Welland had suggested that we use a very flat but amorphous surface, an X-ray mirror actually used for X-ray, focusing X-rays in X-ray telescopes and so on, because this is a flat carbon surface, but it's amorphous. A lot of people had artifacts early on, especially with DNA, because they use graphite, which is obviously highly crystalline, and it has six-fold symmetry. So my molecule also had six-fold symmetry. So if we put it down on graphite instead of an X-ray mirror, we couldn't actually have been sure it wasn't an artifact. But because we were on an amorphous surface, what we saw was going to be real. So that was a good call by Mark Welland to do that. It was lucky. The later measurements were not as easy as the first one, which is always fortunate, I think, because if the first one was bad, you wouldn't have continued. But if the first one is good,
absolutely,
you'll continue, because you know it does work, just not at the moment. So we avoided all. We actually chose not to do much work on DNA because grain boundaries in graphite look very like DNA molecules. It's very unfortunate. The spacing is great, but it's, we were seeing the same structures as people were publishing in Science and Nature, and we knew they weren't real because we could see those without putting any DNA on the surface. So we avoided those artifacts.
Especially if you also say like it was even just the services, like testing and trying,
Yes.
and kind of having a little bit of beginner's luck is always good.
Absolutely.
Especially as nowadays, I think multimodal imaging and data integration is such a huge topic, right, across microscopy. So do you think that also now there's still this strive to add more different modalities into one kind of data set, and how does this impact AFM?
Yeah, I think that's always. I mean, it's always hard to imagine what else you could add, because there are so many different measurements you can make at the same time these days. It's a bit hard in biology for a lot of them. Obviously, the mechanics is okay, and maybe the charge, the Kelvin probe type of measurements are good for biological systems. I think the combination with the optical microscope, when you could have a confocal at the same time to pick up the fluorescence is important, because then you're looking at the right part of the sample, which is, of course, what we don't know with AFM is we don't have any kind of spectroscopy very easily anyway. We can add to it, but it's not immediately obvious from the imaging that you see whether this is the right molecule. So there will be some kind of bias if you're not careful, that you're picking things that look right rather than things that are proven to be correct. So yeah, adding these other modes is important, I think.
I think it's also important to kind of remember that the applications will drive the microscopy and change with the microscopy. And I mean, you've been there from the start. Like, you have seen like the very first kind of applications, the first mirrors and testing and trying in the first samples. And I would love to hear a little bit more about, what you think kind of the initial trends, how they changed to what people are doing now in the field, and what's kind of the most common applications in the last few years maybe that we're seeing.
Yeah. I was thinking about, looking at biological systems in comparison to material science samples. And there's a big overlap, if you think of biological soft matter generally, a lot of synthetic polymers, you've got the same problems as you have with biological samples. But on the other hand, at the other extreme, on very hard materials, we've looked at cellulose, and cellulose is so hard. I mean, if you've ever had a paper cut, you know how hard cellulose can be. And we've got essentially atomic resolution on a biological system because it's so rigid and so immovable, if you like. So I think the trend has been to look at things, especially the glamorous things like DNA, to look at the structure, the helix, the major and minor grooves, the binding of enzymes to it. But I think the big thing that's happened in the biological side over time is first the realization that though we can get three-dimensional images with atomic resolution in aqueous environments, it takes us several minutes to get one image. And in biology, we want to follow processes. And that's what we can do with AFM because it works in liquid. So we need to follow processes at higher speeds. And that's been a goal for many, many years. And I think it came first probably through Toshio Ando in Kanazawa University, who did a heroic development of tapping mode, non-contact mode AFM, to bring us tens of frames a second. We pushed that in a totally different way. We actually sidestepped a lot of the problems that come with using tapping dynamic modes and managed to achieve 1,000 images a second on a collagen sample. But now these things are actually coming into the mainstream, into the commercial instruments like the Bruker machines. These techniques are now there. I think that's the next. We're not seeing so many papers coming out yet. I think people may be a bit nervous of doing it, but I think that's the next step that we need to see. We need to follow processes because that's what biology is all about. It's changes in structure, and the wonderful images of myosin 5 walking down an actin filament from Toshio Ando is probably one of the high points of bio AFM.
It's great to hear about so many different applications. And you have briefly spoken about collagen. And when I was preparing for this episode, I was obviously reading about SEM and AFM. And I was especially taken by the studies on fibroblasts, where basically the collagen is a huge indicator for kind of the inflammatory state of fibroblasts. And that AFM is such a great indicator for the cellular rigidity and the medical diagnostics. So do you think that this is really something that will be taken to kind of medical application and from bench to bedside very soon? Or do you think this is more in the future?
I think it's taken a lot longer than I thought that it would actually get into the mainstream biomedical field. There seems to be still a lot of operator skill, experience, know-how needed. But I think that's getting better, as machines become, more automated in terms of alignment and setup and so on. I think it will get there, but it's a slower process than I expected. It seems that you still need a very skilled operator compared to other optical microscopy techniques, for example. But what the information that's there is certainly very valuable, the fibroblasts, etc. That if you look at life sciences, as I think you will do later in the series, this is definitely a field that's about to explode. I would imagine, because of the techniques that are becoming available to everybody, and you don't have to be an expert to build your own microscope to do them. Though I do enjoy building my own microscopes. So.
Yes, absolutely. So it's so interesting that you say it's not actually the technical challenge from the microscope perspective, but actually the user challenge. So it's more really about the experience, the knowledge, and the application of the people. That's a limitation.
I think so. I think there's a couple of things that you can't do that I haven't mentioned with AFM easily. And if you think of an optical microscope, you switch the lenses around, turn the turret around, and you have low magnification, medium, high magnification, or in electron microscope, or in a scanning electron microscope, you zoom in, yeah? So you say, oh, there's the bit of the sample, there's my fibroblast, that's where I need to go. But in AFM, you have a limited window. Maybe if you have your big scanner on, you have a 100 micron scan area. But maybe you still can't find the sample, the part of the sample you want. And so you're moving around in little windows. And that's where the high speed comes in again. Because now if you can automate that and look at lots of smaller areas and have them all put together into an image, now you can start saying, I can look at this area.
This actually does lead me to the next question, which was, where do you see the future of AFM? Is it more about the automation of acquisition, or is it automated data analysis? Where do you see the future?
Well, I think both of those are relevant. Automation of the machine so that it becomes more widely usable. Data acquisition. Some of my colleagues are using AI, machine learning, to recognize structures on the surface, so that we don't bias our view when we scan a large area and we go and we look for the thing we think we want to see. Maybe we shouldn't be doing that. Maybe we should be scanning large areas and categorizing, letting the AI categorize the structures we see, so we have a more open mind to what might be there. There are a couple of things, really. I'm a big fan of vertical probe microscopy, and I don't think anybody makes a vertical probe microscope, so you got to make your own. But it's where you turn the tip around. Instead of being roughly horizontal, you turn it so that it's vertical, and it's like a spear, so you have a sharp end on it, and you oscillate it about a nanometer at the end, and you bring it towards the surface, and you start interacting with the surface through the water layers. So very important for biology. You feel the surface, but you don't put a force on it. And you can scan over the surface in these water layers and get non-contact images. Some of the most beautiful images. What my previous PhD student, Rob Hardiman, has some beautiful images of DNA. It's come slightly unraveled, and you can see the bases inside. You can see the base pair ladder, just like you see in the textbooks when it's just a drawing. And I think that's non-contact high resolution in liquid, and that's a high-speed microscope too. I think that's one way, but that's not going to happen very much, because if you have to build your own microscope, not many people are going to do that. Another thing that we kind of assume in all this scanning probe microscopy is that our sample is a plane, is flat. And we scan roughly in a plane, and we try to make our sample flat. So we take a piece of mica and we put molecules on it, with DNA molecules. Still pretty flat, just a nanometer or two bump. But biology isn't like that. Yeah, biology is cells and three-dimensional structures. And so we can do something with that, but we're always looking from the same direction, always looking down. We don't look at the side, and we don't look at underneath. And so we tried to make a microscope, as an atomic force microscope, where the probe was not fixed to the rest of the microscope. The probe was free in the liquid. And we grabbed hold of it using optical traps. And we scanned it around the sample, so we could come from the side, from the bottom, over the top, and we could get images of the sample from all directions, always having the probe perpendicular to the direction. And so that's a combination, and I know you have a microscope that has optical tweezers in it as well. So they're probably not holographic ones, but we were using holographic optical tweezers, so we could position our optical traps anywhere. And so we could grab hold of these little micro nano tools that we made and scan them around. So that's a limitation that needs somehow to be broken. I mean, I think all microscopy puts samples down on the surface. I mean, optical microscopy does, and certainly electron microscopy. Everything is in a plane, but life isn't like that. Life is three-dimensional, and we need to develop that further. So that's my 5-10 year window. We've done a proof of principle. It works. It's difficult, but it would be a wonderful thing to be able to look from all directions and create a truly three-dimensional image.
Yeah, life happens in 3D, absolutely. I mean, for example, I've been working in light sheet microscopy, and for me working in 3D, in vivo, it was just amazing to see, brain development.
Yeah, that's a cool technique too. Yeah.
Professor Miles, it's been such an amazing pleasure and privilege to be talking to you today. I've learned so much, and I've made many notes of what I want to read about and what I need to kind of learn about. It's been so, so great to having you with us.
It's a pleasure. I've enjoyed it very much. Thank you.
Well, that's all that we have time for in today's conversation, but join us next time where we will have a discussion with an application specialist to learn more about the many and varying applications of bio-AFM in life science. See you then.
This podcast was sponsored by Bruker bio-AFM, part of Bruker Nanosurface and Metrology Division. Bruker is a manufacturer of scientific instruments for life sciences and materials research, as well as for industrial and applied analysis. If you'd like to learn more, please visit www.bruker.com/bioafm. This podcast was produced by Keep It Science.